Okay, it's a pleasure to have Ferra Valdez from the Center for Mathematical Sciences in Mexico. I'm sorry for not pronouncing that in Spanish.
Don't worry. Thank you very much for the invitation. It's a pleasure to be here, to see so many familiar faces, and to have the opportunity to talk about my work. So today it's about conjugacy classes of big mapping class groups. This is a recent joint work with Jesus Hernandez, Michael Hrusak, Israel Morales, which I think is on the audience, Anja Randecker, and Manuel Sedano. And so it's the first time as well that I give this talk, so it's probably going to be rusty and I think a little bit brutal, because it also has some mathematics that I've been learning recently. So there are many things which I don't completely understand. So let me start in the style of Marco Brunella. Many of you didn't know Marco Brunella, but he used to start his talks by just putting the theorem that he wanted to sell or to explain. So I want to talk about three theorems. I want to read them now, and then I'm going to spend some time explaining the math behind that you need to understand the statement, and then the proof, and then some motivation. So the first theorem tells you, well, if you have an infinite type surface and you consider the conjugacy classes of the mapping class groups of this infinite type surface, then all conjugacy classes are meager. Meager means that you are a countable union of nowhere dense subsets of your mapping class group. I will discuss the topology of the mapping class group in a moment. The second statement is a characterization of dense conjugacy classes. So as you see, this is about the topology of conjugacy classes in big mapping class groups. So an infinite type surface, a big mapping class group, will have a dense conjugacy class if and only if your infinite type surface has no non-displaceable finite type subsurfaces and a unique maximal end. We'll discuss later what does non-displaceable finite type subsurface mean, and what is the order that allows us to speak about unique maximal ends. This is the Man-Rafi order, for those of you who know. And the last theorem that I want to present is the following. Again, now you consider the big mapping class group, and you ask yourself, when do you have a conjugacy class that is dense somewhere? So the theorem before is characterizing where do you have a dense conjugacy class, and now you want to characterize when you have a conjugacy class that is dense in some piece of your big mapping class group. And this happens if and only if your big surface has at most two maximal ends. One case is covered by the preceding theorem. And again, no non-displaceable subsurfaces of finite type. Okay, this being said, I'm going to proceed to explain the math to understand the statements. And before doing that, let me just say that theorem 1 and 2 were also obtained by the different methods by Justin Lanier and Nicolas Blanz. And this somehow summarizes my story on this area of mathematics. Every time I try to do something in this area, somehow someone else already has been thinking about it, and then we coincide at some point. Anyway, I recommend reading Lanier's and Blamy's paper as well. It's also available in the archive because they have a different point of view on how to prove these theorems. Okay. So now let's discuss briefly the topology of big mapping class groups. So there are two ways to put a topology of the mapping class groups, which are at the end equivalent. The first one is, well, since your mapping class group is a quotient by isotopies, you can somehow import the compact open topology from the group of homeomorphisms. This is not what I'm going to do. I'm going to use a more combinatorial way to define a topology. And for this, I need the curve graph. So you consider the curve graph. This is a graph on which vertices are isotopic classes of simple closed curves, which are essential, meaning not isotopic to a point. And now you consider finite subsets of the vertex set of the curve graph. So A represents a finite set of curves. And you define UA as all mapping classes which fix every point in A. Here I put an asterisk in red just to emphasize that I'm considering now the extended mapping class group. I want to put a topology on the big mapping class group, which is the extended mapping class group, which are a whole, I'm also considering homomorphisms that might exchange orientation. So this defines some set of classes, and then the permutation topology is just the one generated by sets of the form F times UA, where F is just an element of your mapping class group. So this is standard when you study permutations of infinite sets. So this is not new. This is something already done. And I put here something to remember me, something that I said, but I want to write, is that it's not obvious, something that you have to think a little bit about, but this coincides with the compact open topology. There is an excellent note by Nicholas Flamis, which I think is called something like the topology of big mapping class groups, on which he discusses in an appendix why these two topologies are equivalent. Okay, so let me comment a little bit about this topology. The first thing that I want to say, but I'm not going to prove, is that if you endow the big mapping class group, extended mapping class group with this topology, then your mapping class group is a Polish group, meaning it's a topological group which is homeomorphic to a complete metric space which is separable. And I want to emphasize this because I think this is one of the good points of view on these subjects. If you have been studying, say, classical mapping class groups, well, you can also think of them as Polish groups, but I think, yeah, that's everything I want to say. So it's a good point of view to think of these guys as Polish groups. So you can put them on the literature of Polish groups and try to extract theorems from there. So maybe the only thing that I want to comment about this proposition is how do you get that this topology is Hausdorff, because this is like something fundamental. So this is a theorem that I want to mention. I will say later on. Well, this theorem you can attribute it to Babar, Dowdall, and Raffi, or in some sense, or you can attribute it to Jesus Hernandez, Israel Morales, and me. We did it more or less in the same time. But for the moment, let me just say that if you consider the intersection of all open sets of the form UA, when I'm thinking that A is a subset of the vertices, which is finite, this intersection is equal to the identity. So this implies Hausdorff for the mapping class group. And this can also be restated in say more the way that Jesus and Israel and I analyze this, as saying that if you consider the natural map from the extended mapping class group into the automorphism group of the curve complex, this is injective. And actually you can promote this to something more, which is, this is not only injective, this is an isomorphism. And from there, once you're in this position, then proving that this is Polish is not that hard. Again, my reference for this will be the excellent note by Nicholas Flamis on the topology of big mapping class groups. Okay, so we have a Polish group. And all the theorems that I said before are with respect to this topology I just described. And now let me discuss the Man-Rafi order. Remember, one of the statements said something like, well, you have a dense conjugacy class if you have a unique maximal order. So thanks for all the definitions that came before, so I don't have to define the space of ends of a surface. So I just want to explain how to put it's not going to be an order formally, but you can think of it as an order. So the definition is the following. This is extracted from a recent paper by Catherine Mann and Castro Raffi, where they introduced this. So I'm going to consider two ends, X and Y. Here, E is the space of ends of your surface. I'm going to say that X is bigger than Y if, well, I'm going to read it. For every neighborhood that you take of X, there exists a neighborhood of Y and a mapping class sending that neighborhood of Y into the neighborhood of X that you chose. I have to add something here because surfaces might have infinite genus, and here is just I have to ask also that this mapping class or this homeomorphism F sends ends with genus to ends with genus. And I'm denoting the space of ends with genus by E superscript G, which is not standard, but this is more the way that Mann and Raffi wrote this. Okay, I'm going to give some examples in a moment, but let me continue with the definitions. So this is just a binary relation. It's not an order. So once you have this, you can define an equivalency relation. You take two ends and you're going to say that these two ends are equivalent or of the same type if X is less than Y and Y is less than X. And I'm going to denote by E of X the set of ends which are equivalent to X. Now, once you have this, you can say now that X is strictly less than Y if and only if X is less than Y and X is not equivalent to Y. And once you have this, then this order that I defined here, this is actually a partial order on equivalence classes of ends. And this is what I'm going to be calling the Man-Raffi order. I'm going to be not that precise. Sometimes the Man-Raffi order will be this binary relation. Sometimes will be the pre-order on ends. Okay, so let us give some examples to have something in mind. So the first example that I want to make is really simple. You take the plane and you puncture the plane at all positive integers. So you have to imagine that you have a convergence sequence to infinity. And so here are the points that you're extracting, 0, 1, 2, and so on. So you can think of this as in the sphere. And it's not difficult to see that in this case, this is the unique maximal end. I'm going a little bit fast here, and this is something that took me time to digest, but Mann and Raffi, they actually proved that the pre-order that I defined has maximal elements, and so I have the right to speak about maximal ends and so on. But if this is the first time that you see these things, I think this is the first and most important example to understand. Every time that you give yourself a neighborhood of infinity, so this is X, and every time that you have any other Y, here you can always find a neighborhood of this Y and a homeomorphism that sends this neighborhood into the neighborhood of X. I didn't say it, but you don't need Y to be sent on the nose to X. You just need Y to be sent close to X. And so this is an example. This is a surface, sigma has a unique maximal end. And so this will be an example that illustrates the second theorem that I mentioned. And just for those of you which are familiar with ordinals, you can identify this example with the ordinal omega plus 1. And I want to say this because once you understand how to associate to this convergent sequence the ordinal omega plus 1, then you can play with ordinals to create a lot of examples. And so I imported this picture from the Wikipedia just to tell you that, well, there are a lot of ordinals, omega plus 1, or omega times 2, and so on. So for example, you can create some other examples, like if you take the ordinal omega times 2 plus 1, and say I want to create an examples of a genus 0 surface, then the space of ends associated to this ordinal will look something like two points, and then you can think of two convergent sequences, one that converges to the point on the left and then the point to the right. So in this case, you will have two maximal ends. And the maximal ends here are this point and this point here. But I mean, you can play with this as much as you want. You can substitute 2 by any number n, and then you will get n maximal ends, and the story goes on. So this is a way to construct different examples of surfaces which have a countable set of ends, always in genus 0. Then you can add genus and maybe accumulate some of these points by genus and so on. So what I'm trying to say here is that to understand the Man-Rafi order, there's a lot of room to play. And so let me just address two more examples. This is an example, I think this is an example by, I'm going to attribute this to Orbez, King, and Rafi, but maybe someone else already thought about this example. This is the avenue of Ximenes. This is an infinite type surface of infinite genus. And so if you want to think of its space of ends, then you will have two maximal ends, and then it looks like omega times 2 plus 1, except that each end is accumulated by genus. And the last one is sort of the first example, say, that is a little bit more complicated, I would say, for grown-ups. But I want to mention it because it's a really nice example that gives you some unexpected results. So this is an example due to Catherine Mann. And the idea is the following. I'm going to construct a surface of genus 0. And in this surface of genus 0, I'm going to play with the Cantor set and some ordinals to construct a really wild infinite type surface. So fix a number k. Let's suppose that k is equal bigger to 1. And then I'm going to draw a cartoon for each n. So for each n, consider the following. I'm going to consider a Cantor set. I'm going to draw this Cantor set as a vertical line. So you have to think of this as a Cantor set. And then in this Cantor set, I'm going to mark k points. So I mark k points. So these are k points. And I'm going to think that these k points, that these are the accumulation points of omega to the n times k plus 1. So you have some countable set here, which I don't want to draw precisely, which accumulates to the Cantor set precisely in these k points. And this countable set is homeomorphic to this ordinal, omega to the n plus times k plus 1. So the idea behind this is that you have some Cantor set with k special points, and this omega to the n times k plus 1 is just some sort of color on which you choose to color this Cantor set with k mark points. And now I'm going to think that this guy is inside some ball of diameter times 2 to the minus n. And this is like my fundamental piece. Once I have this, then as n goes on, so this is for n, as n increases, for n plus 1, I'm going to have, again, something smaller. like a Cantor set that is here, and then maybe, well, your K points. But now they have a different color because here the set that is accumulated to them is omega to the n plus 1 times K plus 1. And I can continue this process, making these balls smaller and smaller and smaller, and make them accumulate to some point that is there at infinity. Okay, so this is the way I construct the surface. I puncture along all these sets that I have constructed. I mean, the Cantor set with accumulation points K, blah, blah, blah. And here, the exercise that I want you to do, if you want to exercise your muscle on the man-Rafi order, is what are the maximal ends here. So why is this example important? It's because this is one of, I call this the man's no AC example. So this stands for automatic continuity. This is something I'm going to discuss in a moment. So this is an example of Catherine Mann on which she proves that the surface that you construct in this way produces a mapping class group which does not have the automatic continuity property, which will be important for this talk. Okay, so so far so good for the man-Rafi order. Really quick, what does it mean to be non-displaceable for a subsurface? Remember, non-displaceable also appear in our hypothesis. So I will say that a surface S contained inside, sorry, this is a mess. So this is contained in sigma. A subsurface S of sigma will be non-displaceable if every time that you hit the surface with a homeomorphism, then it intersects the surface again. So it's what is written, S subsurface of sigma is non-displaceable if for every homeo of sigma, f of S intersection S is different from the empty set. So Javier gave us an example of this in the last talk. So a really nice example of this will be, well, you take some genus 2 surface and then you extract from it a Cantor set. So you remove a Cantor set, so this will be your surface sigma, and a surface that will be non-displaceable will be, say, for example, this one here, S. And it's non-displaceable just because I have finite genus, so every time that I have a homeomorphism, then what is this homeomorphism going to do with the genus? I mean, it has to send it somewhere, but there is no place to send it on the other side, so it has to be somehow stuck there. So this is an example of a non-displaceable subsurface. And if it's the first time that you see this notion, these surfaces, big surfaces having non-displaceable surfaces, they have really special properties, and you can prove many things about them. Okay, so any questions so far? Okay, seems like not. So we can go back to the 3 statements that I gave you and now read them again and have a better idea of what I was trying to say. So now we know the topology. So I'm saying with the first statement that all your conjugacy classes with respect to this permutation topology are somehow thin. They're meager. They don't have, they're meager, period. The second one, now you can understand, well, you will have a dense conjugacy class if and only if you have one of these non-displaceable subsurfaces of finite type, and your surface sort of looks like the plane minus the positive integers. I say sort of looks because I mean, sorry, here what you have, the example that you have to have in mind is that sigma is precisely the plane minus the positive integers. This is a surface with a unique maximal end, and every time that you have something which is finite type inside there, you can always displace it. And the most easy way to see this is that the plane minus the positive integers is the same as the plane minus all integer points. And so there you have a natural subgroup of translations that allow you to translate anything that you want as far as you want. So you can displace anything that looks finite type inside your surface. And well, the last theorem, now you can also understand, so I just leave it there. You'll have a conjugacy class, which is somewhere dense, if and only if now you have two maximal ends, so like these 2 points which are accumulated by a sequence, and no non-displaceable subsurfaces of finite type. So an example of this will be the avenue of chimneys, because you have two maximal ends, and then you can always displace everything by the shift. This figure that I put here has a natural shift. That is shifting, say, this piece to the next one on the right. Okay. Now what? Okay, so I find them. When you study Polish groups, these are natural questions. But to be honest, this is not what motivates us in the first time to study these questions. So let me tell you about what's the motivation behind. And this will help to draw a connection on the methods that we use. So the motivation is the automatic continuity property. So let me recall this property. I will take G, a Polish group. Now I will say that this group has the automatic continuity property if every time that you have a homomorphism from the group G to another H, this is a topological group, which is separable, then this homomorphism has to be continuous. Said otherwise, every time that you have an algebraic morphism between G and a separable topological group, then you have no other choice but to be continuous. And so this property has some consequences for the group G that I don't want to mention, but I will just say it's important to determine when you have a Polish group if this group has the automatic continuity property or not. And so there was a natural question. I mean, when do mapping class group, big mapping class group, have this property? And so we start looking at the literature, and this property follows from another property, which is called ample generics. So let me discuss ample generics for a moment. So if you have a group G, you can consider n copies of G, the Cartesian product of n copies of G. And you have an action of the group G on these n copies by conjugation, coordinate by coordinate. So you will say that your group G has ample generics if for every n, this action by conjugation has a co-meager orbit, or has an orbit that is big in the sense of the topology. So if n equals 1, this only means that your action that you have a co-meager conjugacy class. And you can think of this co-meager conjugacy class as telling you that you have some sort of generic element, which is the one defining your co-meager conjugacy class. So Kehris and Rosendahl, in a paper that I really recommend, proved that ample generics implies the automatic continuity property. So at some point we were trying to say, okay, let's see if we can prove ample generics for some mapping class groups, big mapping class groups, and then get the automatic continuity that way. But as you see from the first theorem is telling you all conjugacy classes of all mapping class group, big mapping class groups are meager. So this property of ample generics fails for n equals 1 for every big mapping class group. So a byproduct of theorem 0.1 is that you don't have ample generics for big mapping class groups. So, okay, there is, you have to look for other methods to prove automatic continuity, and this has been done, or disprove it. This has been done. Catherine Mann, for example, has proven that if you consider the Cantor tree, which is just a sphere minus a Cantor set, so this has the automatic continuity property. And the complicated example that I explained at the beginning with these k points on a Cantor set accumulated by some ordinal, this is a counterexample for the automatic continuity property. Recently, George Domat has also proven that the Loch Ness Monster doesn't have the automatic continuity property. And 2 days ago, I think I saw in the archive, and I think there was a talk in the Big Surf seminar telling you that if you have a genus 0 surface such that the end space is something of the form omega to the alpha plus 1, and I think alpha has to be a successor ordinal, then this also don't have the automatic continuity property. But the question is still open. I mean, we still don't know how to characterize big mapping class group having this property. There's not all of them have them, but it's not clear if, so for example, infinite genus, it's a way to kill this property or not. So this was our motivation. And now I think I have around 19 to 18 minutes. So I want to spend the rest of the talk trying to explain how do you prove a theorem like theorem 1, theorem 2, or theorem, the 3 theorems that I put on the slides. I want to concentrate on this one, the characterization of dense conjugacy classes. So I recall the theorem. If you have an infinite type surface and its big mapping class group has a dense conjugacy class, if and only if sigma has no non-displaceable finite types of surfaces and a unique maximum. So yeah, how on earth do you prove something like this? Long story short, the methods that we use are contained in the following paper that I really recommend reading. Maybe I shouldn't recommend it actually, but I will do that. And the methods are extracted from this paper. So this is a paper for me. When the first time I saw it, it's a paper from another planet. It's a paper on model theory by Kehris and Rosendahl, on which they give you the tools to show that something has a dense conjugacy class and much more. But I want to point my finger on this paper because I think this is the paper to read if you want to study your favorite Polish group. You have your Polish group and you want to prove something about this Polish group, like having a dense conjugacy class or a meager conjugacy class. So the methods here are the ones to you, the ones that will help you. Also for the automatic continuity and so on. So going back to my presentation, the sketch of the proof uses a theorem by Kehris and Rosendahl. So let me put it here. It's a theorem by Kehris and Rosendahl. And just going to read it. So the theorem says the following. If you have a Frese class K, whose Frese limit is this bold K, then the following two are equivalent. First, there is a dense conjugacy class in the automorphism group of bold K. And second, K sub P satisfies the so-called joint embedding property, which is abbreviated by GEP. So of course, I don't expect anyone to understand what I just said. It looks like some really mambo jumbo that I have to make sense of. I mean, how I'm going to use this? What is a Frese class? What is a Frese limit? How do I use this for big mapping class groups? So I'm not going to give a crash course on Frese limits and Frese classes, but the idea when you have such a statement is that you would like to put here, I mean, you read it without your glasses and you just see, okay, dense conjugacy class in automorphisms of something. So what I would like to do is to put, instead of out of K, I would like to put here the mapping class group of my surface. So if I'm able to make sense of this theory and then replace out of K by mapping class group of sigma, then I'm in good shape, because then I only have to understand what this KP thing is and what is the joint embedding property. So I will say the main contribution that we do in our work is basically a translation work. We take this theory of Kechlus and Rosendahl and then put it in the language of surfaces, mapping classes, homeomorphisms, and then check that, well, KP satisfies the joint embedding property. So let me discuss now a little bit how you do this and what are the objects, and without talking a lot about Frese classes and Frese limits. So the first thing that you have to understand are structures. So what is a structure? Here is a definition. So structure is a word that you abuse a lot in mathematics, but it has a precise definition in model theory. So you need a set, which is called the universe. You need a signature. A signature is some sort of abstract relations that you define on this set. And this is abstract because you haven't materialized them. And then every time that you have one of these relations, you have a way to interpret this relation. And this interpretation gives you an actual n-ary relation, meaning that you have a subset of some power of your universe. So this looks abstract, but let me give you an example of a structure that you know. So let's say that now K, instead of just being some abstract set, is the set of vertices of your curve complex. So this is my set. So what will be an abstract relation? An abstract relation would to say that alpha and beta universe are related if and only intersection alpha and beta. So this is the abstract relation telling you when two vertices in the curves will be adjacent. Interrelation of when you C0 sigma times C0 sigma, the actual interpretation of that relation will be the subset here containing all edges of the curve graph, sorry. Okay, so this defines a structure, bold K, which is the bold K that appears here. There is a technical issue which is hidden in the words Frese limit and Frese class that I'm going to skip for the moment. We can discuss that later. But for those of you who know, asking K to be the Frese class means that the structure you're considering has to be ultra homogeneous. And this means that if you take two finite substructures of your structure in them, you can actually promote that guy to a global automorphism. So for the moment, I have to skip that technical part. And so what I want to say is, here's again the theorem. Modulo imported technicalities, I can actually replace out of K by the mapping class group, and just here, K, what will be K? K will be the curve graph, but I have to enrich it a little bit from plus some extra elements in the signature. So if you haven't seen this before, just ignore it. If you haven't seen it, well, you can always enrich the curve graph to get an ultra homogeneous structure so that you can.
All right.
Yes?
It's not extended mapping class group, or you can make it a mapping class group?
Good question. Excellent question. You can make it actually of the extended mapping class group. So this is a whole process called falsification. If you give me the curve complex and you give me a closed subgroup of the mapping class group, I can put this in a machine that produces an ultra homogeneous structure, automorph the group that. So I'm saying more, but the theorems that I presented are actually the simplest versions of these theorems. These theorems are valid for a larger class of closed subgroups of the extended mapping class group. So a particular example of a closed subgroup of the extended mapping class group is the mapping class group itself.
Thank you.
Okay. So in the last 9 minutes, let me just go really, what is the class KP? The class KP is the following elements in that. You have to think about them actually as finite bits of homeomorphisms. So what are these? So I wrote too much here, but you have to say B and C are two finite substructures of your curve complex, this enriched curve complex, and psi is isomorphism between them. A, here's just some noise, it's just some reference. Ambient finite structure contains B and C. So class KP, shortly said, is just the class of, I will say, finite bits of homeomorphisms. Homeomorphisms or mapping classes, or if you preferred, automorphisms of your structure K that I haven't defined. Once you have them, then you can say when one class embeds into the other, because remember, I'm trying to use this theorem that KP satisfies the joint embedding property, so there must be some notion of embedding behind. So I will say that a class in KP represented by a finite bit embeds into another if I can find an isomorphism between the union of the domains of these finite bits, the union of B and C into the union of B prime and C prime, which sends B to B prime, C to C prime, and makes the following diagram commute whenever this makes sense. In this case, will make sense everywhere because I'm not considering A. So said shortly, there is a notion of embedding from one class into the other. And once you have this, you can define the joint embedding property. The joint embedding property tells you the following. So the joint embedding property tells you the following. Every time that you have, I'm going to put quantifiers now. For every two finite bits of homeomorphisms or automorphisms, C and C prime, that you have, there always exists a bigger one that I'm calling CB prime, BB prime, C prime, and two embeddings, F prime and FB prime embeddings. So the joint embedding property is telling you every time that you have two elements in this class, you can actually find a bigger one on which they embed. And in the sense that I just defined before, which was a little bit fast and difficult to digest, I guess, but the main idea is that you have a class, you have to take two pieces, and then there should exist a bigger piece on which you can embed both. So this is really abstract right now. So how do you translate this into the language of surfaces? I mean, at the end of the day, you want to prove something about big surfaces and big mapping class groups, but you ended up in this abstract world with these abstract properties. So the translation of all these, how do you say, collage or salad or whatever, is the following in the languages of surfaces. So what do you have to prove at the end to get the joint embedding proof property and get that your mapping class has a dense conjugacy error? So this is one of the main results, I will say, but it's just a technical lemma that we prove, but I will say it's one of the main contributions, is the interpretation of all this abstract thing into the language of surfaces. So you have to prove the following. Given two finite types of surfaces, S and S prime of your big surface, and any two mapping classes. Here I put gamma, but actually gamma, you should think of gamma as just being an element of the big mapping class group. You can find 3 other mapping classes such that the following happens. So let me just draw the diagram. You have your surface S that you have given to me, and then H, which sends H to H of S. These are finite types of surfaces. And then here you have S prime, H prime, H prime of S. And the joint embedding property in this language just means that you can find 2 homeomorphisms or 2 mapping classes G and G prime, which conjugate this finite bit. This is like a finite bit of a homeo. It's restricted to a finite subsurface. So this will send it to JS, and then, well, here to where it corresponds, J prime of S prime, here to where it corresponds. And a guide that fits here is the same guide I'm putting here in the same color, which makes these 2 diagrams commute up to isotopy. So that's it. If every time that you give me 2 finite types of surfaces and 2 homeos, you can find 3 others making all these things commute up to isotopy, then you will have that the joint embedding property is satisfied for the automorphism group for FP, for the class FP coming from the enriched curve complex. And so this is what we did. I only have 4 minutes, so I'm going to skip what it's next, which is, what's the ideal situation in which you can do this? But long story short, the ideal situation is given by a surface on which you have no non-displaceable surfaces and a unique maximal end. In that setting, you can show that this is satisfied. And skipping that by reasons of time, sorry about this, I'm going to skip that to go to the last part of my talk. So in the last part, I'm skipping this part. This is illustrative case, how you can do it, blah, blah, blah. And maybe say some words about how you prove the first theorem that all conjugacy classes are meager. Well, the idea is that you have a similar definition. The similar definition is another property that is not a joint embedding property, but something that these guys call the wake amalgamation property, which you can formulate as is written here. Don't try to read it, it's just too technical, but the idea is that you read the property in their language, you translate it to our language, and then you check that you can actually check this property in our language. And this is what we do. So I'm skipping this. I'm just pointing out that there is just the same kind of trick. It's just another property. And let me finish with the last comments on what is left and some like interesting remarks. So this is in the last 2 minutes. So some remarks, final remarks. So for the theorem that characterizes dense conjugacy classes. So remember, map of sigma has a dense conjugacy class if and only if no non-displaceable subsurfaces of finite type and a unique maximal end. So this was a theorem. So the remark that I want to make here is that if the genus of your surface is equal to 0 and you have that the end space of your surface is countable, which are the surfaces that have a unique maximal end? So this will be surfaces for which E is homeomorphic to the ordinal omega to the alpha plus 1. And this is a strange coincidence, but this is precisely the surfaces. These are the surfaces sigma for which you have that the mapping class group of the surface is quasi. I'm going to abuse language, but it's quasi-isometric to a point. In the language of Mann and Rafi, the mapping class group is cursorly bounded. So I don't know if this is only a coincidence or is there's a deeper connection here. And the other thing that I wanted to say is that, let me go back to the main theorem that I had here. Sorry. This theorem that we proved here is stated for the mapping class group, but it actually works for a larger class of groups. This is related to Ruben's question. And so it works for, this remains valid if we substitute the mapping class group of sigma by gamma, a subgroup of the extended mapping class group closed, and then let me say with enough dent twists. What do I mean by enough dent twists? It means that every time that you consider a simple closed curve, then this group gamma will have a non-trivial power of a dent twist with respect to that simple closed curve. This might be like the 7th power, but yeah, that's the definition. So this allows you to prove that you have dense conjugacy classes actually in a lot of smaller big mapping class groups, not just the mapping class group itself. So I finished my talk here with the, let me wrap up. So there are these natural questions about the topology of conjugacy classes on Polish groups. There is this general abstract machinery coming from model theory. And maybe my last comment will be, I didn't believe in model theory before, but it's actually a really powerful tool to prove things about Polish groups, in particular, big mapping class groups. So thank you for your attention, and an excuse for being maybe a little bit brutal with all this.
Thank you. Do we have questions? Any questions? I have sort of a side question.
Okay, go.
Sideways question. It has to do with the mapping class group of those special spaces, which was the mapping class group being quasi-isometric to a point. Right. The Rafi, you said, was it Mann-Rafi's theorem? I don't remember.
Yes. So
okay.
Mann and Rafi, the paper on which they define the order, it's actually motivated by the question of what is the quasi-isometry type of a big mapping class group. And in order to make sense of this, you have to have some properties, and they actually show that for genus 0 surfaces for which the space of n is countable and has this form omega to the alpha plus 1, then your mapping class group is corsally bounded, meaning that there are many definitions of this, but basically any action of your mapping class group is on a space will have bounded orbits. And yeah, I don't know if I answered your question.
Yeah, I think, well, the reason why I get confused when I see quasi-isometry in this context is that the mapping class group is infinitely generated.
Yes. Maybe
right.
let me put this properly. So it's CB. It's corsally bounded. It's infinitely generated.
Okay.
So
okay. I see. Okay.
It's corsally bounded. Yeah.
Yeah. Oh yeah, that's the point. Okay.
But even if it's infinitely generated, you can still make sense of the quasi-isometry type of the group. And this is one of the main points that they make. I mean, a priori you can't, because the word metric depends on the generator set that you choose.
Right.
But sometimes you can. And this is the content of a theorem of Rosendahl, which it tells you if you have a neighborhood of the identity, which is CV plus a CV generating set, then you can make sense of then any two-word metrics with respect to two CV generating sets will be quasi-isometric. So it makes sense to speak of the quasi-isometry type.
Okay.
Yeah.
Okay, that's the point. Okay, I see. Right. Okay, thank you.
And before any other question, let me just, being the last, how do you say, el último toro de la tarde, the last bull of the afternoon. Thank the organizers. Let me thank name of all the organizers for all the work and putting all these things together. And let us give them a big clap.
Well, I have to say, before I hand it over to Ruben, this was quite easily quite literally the easiest conference I ever organized. Let me put it to you that way.